Okay, this is a list of all of the chemical reactions that we have talked about all year. We started with a whole unit on chemical reactions back in January when we talked about single replacement, double replacement, synthesis, decomposition, and combustion. Okay, but here we are, I'm including even the nuclear reactions, I'm including the specific ones like redox, I'm including neutralization, as well as all of those organic reactions that we just did. So I won't spend too much time on those because you already know so much about them. I'm going to start with single replacement. Single replacement, you need to use table J to see if that single replacement reaction can happen. A single replacement reaction starts with something by itself, something alone, like barium in the presence of a compound, like sodium chloride. What happens is that barium decides to come over and take sodium's date. Barium has to be cooler than sodium, more popular, more active than sodium. In this case it is, it's higher on the chart. Therefore barium is going to take sodium's place. Make sure you flip-flop and get the right formula, leaving sodium out in the cold. That is a single replacement reaction. You're looking for something alone, taking the date and switching, and something else being left alone. Nonmetals can do this too, okay? We could have something like fluorine plus NaCl. It's not going to be sodium alone anymore. Fluorine and chlorine are in the same group, so they behave the same way. So fluorine's trying to take chlorine's date. Fluorine is way cooler than chlorine, so fluorine can do that. And we end up with NaF and Cl2 left out in the cold. All chemical reactions should be balanced. I'm just not doing it for the purposes of this slideshow, so I apologize. But I don't want to make you sit there while I balance these as well. Double replacement, they switch partners. The overall thing for double replacement is AB plus CD goes to AD plus CB. Remember, the positive one should be written first, so A is positive and C is positive. Always write the positive ones first. Just switch the partners. Take these two and flip-flop them, okay? A neutralization reaction is a double replacement reaction. You're looking at table F for this. Table F will tell you if this reaction happens. One of these two needs to be insoluble. That means on the middle two columns here of table F in order for this reaction to happen. That's the precipitate, that's the solid. Synthesis is putting something together. You only have one product. It's AB goes to A plus B goes to AB. Decomposition is the opposite. You only have one reactant and it falls apart into its components. Oftentimes, synthesis and decomposition are redox reactions. Not always, but often. These are all kind of standard chemical reactions. Sometimes they're called table talk. We do these in lab, or like lab bench. Important to note is that every single chemical reaction that we do will conserve mass, charge, and energy. Sometimes mass will be transferred into energy, but the overall will be the same. Okay, so we're conserving mass and energy as well as charge. A decomposition reaction that we have done, that we just did in lab, is H2O2. Decomposes into H2O and O2, an oxygen gas. If I balance it, there we go. And a synthesis reaction that you might see would be PCl3 plus Cl2 goes to PCl5, something like that. Okay, this would be synthesis, and this is your decomposition example. All right, nuclear reactions are also chemical reactions. Okay, we talked about natural transmutation and we talked about artificial transmutation. Transmutation means you have a new element. That means that nucleus, this is the reactions of the nucleus, the protons and neutrons, is changing. It's mutating into something else. Natural transmutation only has one reactant, and goes into 2 or more products. Okay, it completely changes. Artificial transmutation has a plus sign on the left side, a more than one reactant, and ends up with probably more than one product as well. The key to these is that they are nuclear reactions, so it's not going to be something like NaCl anymore. No way. We're looking just at the nucleus. So when you're looking at beta decay, it's spitting out a beta particle. What's a beta particle? It's an electron. It looks like that, okay? Alpha decay, it spits out an alpha particle. An alpha particle is a helium nucleus. It looks like this. This is your charge or number of protons. This is your mass number. That's how heavy it is, okay? Beta decay, some things that undergo beta decay. If I'm looking at my reference table, which I was not, but here it is. Beta decay, gold 198 undergoes beta decay. Let me erase my NaCl. Here's AU. AU, give me all your gold. 198. Gold is number 79. It's natural transmutation, and it undergoes beta decay. So here's my beta particle. You can write a beta or an electron, whatever you want to do. Then to figure out what is left, you need to do a little bit of math. The numbers on the top have to be the same on both sides, and the numbers on the bottom have to be the same on both sides. So what's the number on the bottom? It's 79 over here. So x minus 1 has to equal 79. That's 80. Look at your periodic table. Number 80 is mercury. So that's where the symbol comes from. You would do the same thing for alpha decay. Something that undergoes alpha decay is radium-226. Radium is number 88. Arrow, natural transmutation, so only one reactant. Alpha particle plus 226 minus 4 is 222. 88 minus 2 is 86, and that's radon. So 86 plus 2 has to equal 88. That shows the conservation of mass and charge. Fission and fusion are two specific types of artificial transmutation. They are not the only types, but they are two specific types. They both, all of these nuclear reactions convert lots of mass to energy. They don't convert, I guess that's wrong. Forgive me. They convert mass to energy. They are super exothermic. They release way more energy than those other ones, than the ones we just talked about. Fission, you're going to start with a uranium nucleus, number 92. You're going to hit it with a neutron. And you're going to end up with two smaller nuclei, maybe like krypton and I don't really know, barium. And you're going to spit out 3 neutrons. These 3 neutrons go on to hit 3 more uranium nuclei, which each have 3 coming out, okay? So that's your chain reaction of nuclear fission. Lots and lots of energy from this. But you also get lots and lots of energy from fusion. Fusion, you have only little baby light ones, like hydrogen, plus maybe a deuteron, which is hydrogen 2. You put them together, and you end up with helium 3. 2 plus 1 is 3 over 2. Plus crazy energy. We would love to be able to do this on Earth. We would love to do fusion on Earth, but we can't. We don't have it. We can't get these 2 nuclei together because they're so positive. They repel each other, and they're so tiny, they're hard to control. So if we can get the pressures high enough and the temperatures hot enough, we could get those together, and we could get crazy awesome energy from nuclear fusion. This happens in the sun. It does not happen on Earth. All right. Organic reactions. Do we have another one here? Okay, I'm going to switch to specialty reactions and then I'll go back because I don't want you sitting there for too much longer. Redox reactions. You have a change in oxidation state. The oxidation state changes of two different things. Usually it's going to be something like combustion. It's going to be single replacement. You're looking for something by itself. Ending up in bond. So this is by itself. It's zero oxidation state here. It's not zero here. So that's redox. Neutralization is an acid plus a base equals water and salt. A salt, not NaCl. Okay? This is just double replacement. Just double replacement. So an example here is HCl plus CaOH2, calcium hydroxide. Hydrochloric acid plus calcium hydroxide gives us water and calcium chloride. Clearly you would balance it, but I'm not going to waste your time. Last slide, organic reactions. We're going to go through these really fast because we just did this. I'm going to start at the bottom and work our way up. Saponification makes soap. It also makes glycerol. Glycerol looks like this. It's a triol. That means it has 3 alcohol groups. This is a triglyceride, which is an ester. How do you know it's saponification? Because there's a big honking base there. NaOH, KOH. When you see that in an organic reaction, that means that carbony stuff. That means you're making soap. Polymerization, you're starting with monomers. Things that are just one, any number of them, probably a ton of them. And then you make a big long chain of them. You make them all connected to each other like this, and that repeats countless times. Changing color. The esterification we did in lab, this is organic acid plus an alcohol, gives you an ester plus water. If you need to look at your lab again. We did this one in lab. Esters smell good, okay? The OH from the alcohol group and the H from the organic acid come together to form water, and the other two stick together forming an ester. Remember that an ester you can find on table R, okay? I'm going to erase that so that I can write about fermentation. Fermentation, you're looking for zymase or a catalyst, okay? You're starting with something like sugar. It's usually glucose. It's not always. Here's your zymase, excuse my awful C. And it's turning into ethanol. This is alcohol. And CO2, carbon dioxide. Combustion. Combustion. You start with something carbony in the presence of oxygen, something organic with oxygen. The products, Jared, the products of combustion are always CO2 and H2O. Always, always, always. Carbon dioxide, if it's incomplete combustion, it might be carbon monoxide, but if it's a combustion reaction, it ends up in carbon dioxide plus water. Finally, substitution and addition. Substitution starts with an S, so you start with a saturated hydrocarbon. That means it has all single bonds. Look at all those S's. Look at this lovely alliteration on a Thursday afternoon. You're going to replace them. You have two reactants and 2 products here. That's how you know it's substitution. You pluck a hydrogen off, and you put the halide usually where the hydrogen was. There's no double bond to break. Addition is the same as a synthesis reaction. You start with a saturated hydrocarbon like this. You start with an unsaturated hydrocarbon. Saturated is substitution. Plus a halide. You don't substitute anything. You actually add the bromines to each carbon. So each carbon now looks like this, with a bromine and a bromine. Okay? Each carbon now looks like that. All right? 15 minutes is a long video. I apologize for this one being so long. The last thing I really want to talk about quickly is exothermic versus endothermic. Here is your reactant. Here is your product. All right? Exothermic reactions, the heat exits. The heat is released. It's over here. The energy, NRG is energy. The energy is on the product side for exothermic reactions. Okay? For endothermic reactions, the heat is absorbed plus energy. It's on the reactant side. It's absorbed. It goes into the reaction. Okay? So this is your endothermic. You do need to know the difference. If the regents ask you a question about a reaction and there's energy on either side and you're not sure if it's addition or substitution, but they tell you that energy goes in, you can always say it's endothermic. Just make sure you get it right. All right? Okay, fabulous.